All right, guys. So we'll talk about the rational root theorem and then finding zeros of polynomials. We'll stick with finding real zeros for now. But let's do a little warm up first, a little review. Let's say we have f of x equals x cubed plus x squared minus 4x minus 4. Can we divide that by x minus 3? Okay, and we can, right? That's something we have covered. And since we're dividing by a linear binomial here, right, this is the kind of thing we want to use, or we want to use synthetic division on because it's usually quicker. But again, you could always use log division if you prefer. But with synthetic division, since we're dividing by x minus 3, we're going to go ahead and put a 3 in the box. Okay, remember it's the opposite. If you divide by x minus 3, you actually use positive 3. Then we do the coefficients from the f of x, so 1x cubed, 1x squared, negative 4x, and negative 4. Okay, and then we will just do our little synthetic process where we always bring down that first term and then we will multiply by what's in the box. So 1 times the 3 is 3. And now we add straight down. 1 and 3 is 4. Multiply that by the 3 and we will get ourselves a 12. Negative 4 plus 12 is 8. 8 times the 3 is 24. And negative 4 plus 24 is going to get us 20. Okay, so that means the answer to the division problem that we just did is, if we started out with x to the third power, right? So we're going to end up, our answer will always be 1 degree lower than that when we divide by linear. So these here are the coefficients starting with 1 for the x squared, plus 4 for the x term, plus 8. And then our remainder is positive 20. And it goes over the thing we divided by, which was x minus 3. Okay, so this would be the answer to the division problem as a little review. Okay, so let's take a look over here. Can we now find f of 3? Okay, so f of 3 is basically just saying plug in 3 for the x value into f of x. Okay, right, so I'm just typing that into a calculator to verify real quick. I'm actually putting it in y equals, and I'm going to use the table feature. Okay, and when I did that, f of 3, oops, let me get a marker here, f of 3 ends up equaling 20. Okay, is there any sort of connection with the remainder there and the value? Let's see. All right, let's do another problem. Let's divide f of x by x minus 2 now. Okay, so down here. So again, when we're going to divide by x minus 2, I'm going to use positive 2 in the little synthetic box. Same coefficients, 1, 1, negative 4, negative 4. Okay, and when we do this, we will again do the same thing where you bring down the first term, and we're going to start multiplying. So 1 times 2 is 2. 1 and 2 add up to 3. 3 times the 2 over there is 6. Negative 4 plus 6 is 2. 2 times 2 is 4, and negative 4 and 4 is 0. Okay, so that's going to be our remainder there. So this time, the answer to the division problem, again, coefficients are down here, starting with x squared. So x squared plus 3x plus 2. This time we have no remainder. Okay, so that means it went into it evenly. And just verifying on my calculator, f of 2, I can see that f of 2 actually equals 0. Okay, and again, take a look at that. Look at our remainder here, and look at the y value there. Okay, and there's a reason for that. It's a property. What we kind of did, or what it's called synthetic substitution. And so, imagine if you had to do a problem like this, or like this, where you're finding f of a certain value, and it's probably a lot more useful before we had powerful calculators, but it might be easier to just say, all right, if I need f of 3, for example, I can just stick a 3 in the box here, do my little synthetic process, because all this process is addition and multiplication. And then whatever the answer is, that's going to be the y value. Okay, that might be easier back in the day instead of plugging in a number into the original expression, especially if the exponents were really large, and it wasn't easy to do the calculations by hand. Okay, now with the graphing calculators and stuff, it's really not a big deal to just put the equation in and calculate the y value. But synthetic substitution is a thing, and it does have some tie into what we're going to be doing. Okay, so let's see, can we completely factor the original f of x now. And let's think about what we did in part C here. When we divided by x minus 2, okay, and we got this answer right here with no remainder, okay, that means, let me just rewrite f of x. The original f of x was x cubed plus x squared minus 4x minus 4, right? And when we divided it by x minus 2, we got this quotient here, okay, with no remainder. So that means that x minus 2 is a factor, right? If something divides in evenly, it's a factor. And the other factor is what we got when we did the division problem, right? I mean, division kind of gives you the factors. And now the only thing we need to do, can we factor this any further, is x squared plus 3x plus 2 factorable anymore? I think it is, right? X plus 2 times x plus 1. Okay, that's just looking at this and being able to factor it into those two like an old school quadratic problem. Okay, so now that we have that, we could easily find the zeros here, right? We know that positive 2 was one of the zeros when we did this step right here. But now that we have this thing in factored form, I can see that negative 2 is also 0 and negative 1. Okay, so sometimes you just need to find one factor to get the ball rolling, and then you can do division and then keep factoring. And that's kind of what we're going to be doing in this section to find the zeros. All right, let's go through an example. Let's say we want to find all zeros of a polynomial function, okay? And we want to have nice exact values. So I don't want to just totally rely on a calculator and getting decimals and all that stuff. Okay, so I have a graph here. I just threw this in decimals. Okay, and using a graph is going to be really helpful to get the ball rolling sometimes, but you're still going to need to know how to do some things algebraically as well. Okay, a couple things I want to point out. The original f of x, right, is a 4th degree polynomial. Right? Its highest exponent is 4, and we see there are 4 zeros showing up on the graph. Okay, so that means that all 4 of the zeros, because it's going to have 4 total zeros, because that's the degree, all 4 of them are real, because they're all on the graph. Okay, at some point we will see some problems where you might only see 1 or 2 real zeros, but there's 3 or 4 out there, or even more. Okay, but for now they're all showing up on the graph, so we want to get some values. So one thing I noticed specifically on this problem, each term in the original f of x has a common factor of x. So let's bring that out. Okay, anytime you have a common factor, it's going to help to factor that out first and just make the problem a little bit smaller. So each of these are going to basically lose one of their factors of x. Okay, so we're going to have x times 5x cubed minus 33x squared plus 53x minus 21. Okay, and what that helps also with is now that this is factored, remember when you can set each factor equal to 0, this first factor of x here can be set equal to 0, and that's going to give us one of the zeros immediately. And that one we see is right here. 0 is a 0. So what we need to now do is just focus our attention on this and find the other 3 zeros. And we're going to try and do it by factoring. Alright, so let's just pretend like our problem now is just this. 5x cubed minus 33x squared plus 53x minus 21. Okay, and we need to find the 3 zeros on that. Okay, so there is this thing called the rational root theorem. Okay, it's not super useful because again, with the calculator technology these days, we kind of don't even need to mess with this, but I just want to show it just to kind of put it out there. But what it says is that if we were to take, what we're going to do is make a list of possible rational zeros, just to give us some options. And then I'll show you the process we need to do. But to get the list of possible rational zeros, okay, because it looks like when you look back at the graph, you know, none of them appear to be nice whole numbers, but there could still be some rational ones. And the point is, we need to get a rational zero so that we can then divide by its factor. So let me take a step back and show you how this works. So we're going to look at the constant term here, and we're going to look at the leading coefficient to do this. Okay, so what we do is we list all factors of the constant term. Okay, so of the negative 21, the possible factors are 1, because 1 goes into everything, so I'm just going to make a list. It could be positive or negative. 1, 3 goes into 21, 7 goes into 21, and of course 21 goes into 21. And each one of these could be negative or positive. That's why I put the plus or minus. And then we put in the denominator, we put the factors of the leading coefficient of 5. Okay, so what this is doing, it's giving us a list of possible rational zeros, and I'm just going to expand the whole list this first time. And again, you'll see it's kind of a pain to do this process, but I just want to put it out there. But I'm going to take every combination, meaning 1 in the numerator and 1 in the denominator. If it's the 1 in the numerator and the 5 in the denominator, it could be 1/5. Okay, then I'm going to move to the 3 in the numerator. It could be 3 over 1 or 3 over 5. It could be 7 over 1 or 7 over 5. And it could be 21 over 1 or 21 over the 5. Okay, and again, all of these could be positive or negative. And what we really did there, we just made a list. Okay, and what it's just telling us if there are real zeros, rational zeros, it's going to be one of these numbers. Okay, so what you would do is you could, back in the day, before you had a graphing calculator, you could check and say, all right, is 1, and just start going through the list, is positive 1 a 0? This one on the graph, you can kind of tell it's not. Okay, is negative 1 a 0? No. Is 1/5? Well, it might be. Okay, so you would either have to plug in 1/5 for x and see what the y values are, but that's when you could also use that synthetic substitution I was showing you. Okay, in the warm-up. So let's say, just to save some time, it's not 1/5, it's not positive 3. Okay, this 3/5 looks like it might be that 0 right there, right? So let's try it. We're going to check 3/5, okay? Or what you could do is graph the thing, find the 0, okay? And if you know that it's 3/5, you can use that. But here's what we're going to do, okay? Let's say we did that. Let's say we graphed it. And let's say we know that x equals 3/5, okay, it might show up as 0.6, is a 0. Okay, what we're going to do with that is then we're going to use synthetic division. Okay, because if 3/5 is a 0, that means that x minus 3/5 must be a factor. Okay, and if we know one of the factors, we are able to find the other ones. Okay, so here's what we're going to do. We're going to take that 3/5. Okay, and I'm going to divide it into this. I'm going to divide that expression by x minus 3/5. So I'm going to put 3/5 in the synthetic box, right, because we always use the opposite. Then we're going to do the coefficients of 5, negative 33, 53, and negative 21. Okay, and we're just going to divide this down. Now note, I'm doing this with this version here. Okay, the one where we already factored the x out. Okay, so I'm doing it with the 3rd degree. So when we do our little process, we bring down the 5, and we multiply 5 times 3/5 is just going to be 3. Okay, negative 33 plus 3 is negative 30. Okay, negative 30 times 3/5 is, and I'm just making sure I do this accurately on the calculator, is going to be negative 18. Okay, 53 and the negative 18 add up to be 35. 35 times the 3/5, okay, or 0.6 is 21. So our remainder is 0. Okay, now that's a good checkpoint here. Okay, remember we said that, and we kind of went to the graph and we said we know 3/5 is a 0, right? Either use your calculator or use Desmos to get the 0. But this kind of confirms it, right? Remember what we said in the warm-up? That gives you the y value. That's that process of synthetic substitution. Okay, so that gives me confirmation that 3/5 really is a 0. So the bigger thing is that it tells us now that the answer we got, okay, which is 5x squared, remember the bottom row of coefficients, minus 30x plus 35 is a factor as well. Okay, it's a factor of f of x. So what we can do is we can use that now to find the other zeros, and we can find them as exact values using the quadratic formula. Okay, now some of you guys might be thinking, and I kind of hope you're thinking, why couldn't we just go to the graph? You know, if we got the 0.6 from the graph, why can't we just get these from the decimals and call it a day? Okay, it's a good question, but the issue is we need to have exact values, okay, and chances are these are going to be irrational numbers. Okay, so you're just going to get some decimal approximate from your calculator or from decimals. Now, if they were nice rational numbers, that's fine. Don't have to go through all this. But a lot of times they're not. Okay, and in this case, they're not. You could be able to see that if you graph them. But we will be able to get those exact values solving this by the quadratic formula. Okay, so we're going to set, let's use the quadratic formula. Okay, or you can try factoring, but usually if it's not a rational number, the factoring may not work. But let's do quadratic formula. 5x squared minus 30x plus 35 equals 0. Okay, if you recognize that you can factor a 5 out, make the numbers even smaller, that's going to help a little bit. Okay, you can factor that 5 out, because then when you divide both sides by 5, you just get x squared plus minus 6x plus 7 equals 0. Now's where we're going to actually go into the quadratic formula, which says x equals the opposite of b plus or minus, right? Square root of b squared minus 4 times a times c all over 2a. Okay, which is going to equal 6 plus or minus, let's see, what do we have under there? 36 minus 28 all over 2, okay, which is 6 plus or minus, so 36 minus 28 is 8 over 2. And now we just need to keep on simplifying. Oops, I'll move this whole thing up, give myself some room here. So the square root of 8, remember how to break these down. Look for perfect squares that go into both, or that go into it, I mean. So root 4 times root 2, which is 2 root 2. So we have 6 plus or minus 2 root 2 all over 2. And then since each coefficient is divisible by 2, we can split it up and reduce one final step to get our final answer of 3 plus or minus root 2. Okay, now those are the exact values of the other zeros that the graph showed. Okay, they're going to be irrational numbers. If I just throw it in my calculator, 3 plus root 2 is, as an approximation, is like 4.14 something. 3 minus the root 2, 1.59. Okay, so those would show up on the graph, but writing them as a decimal is just not considered exact. Okay, these are nice exact final answers. So all real zeros, just to put this all together. Let's see if I can zoom everything in a little bit here so we can all fit on one page. Final answers are, from the very beginning, we had x equals 0. Okay, we had x equals 3/5, which is the one that we saw on the graph. That's the rational one. And then we had 3 plus and minus root 2 as the other two. Okay, remember the plus and minus means there's two answers there. Okay, now here's the deal. We needed a rational root, okay, while we went through this whole process where we made that list right here. We needed a rational root to do the synthetic process. I could not have done that with one of these guys, because these are decimal approximates. They're not the actual full root. Okay, so that's kind of how that works. I will walk through one more example with you guys. So let's do it. All right, so let's walk through one more of these. This one's a nice big 5th degree polynomial. So we can see, again, I threw it in decimals as I love to do. We can see there are 5, 2, 3, 4, 5 real zeros showing up on the graph, okay? Some of them are going to be rational numbers, some of them not, and the thing is we need to write them all as nice exact values. So we're going to try to find a rational one, at least one, to get the ball rolling. Okay, so let's take a look. From the graph, it appears -1 might be a 0. Okay, so you'd either have to verify that on your calculator or Desmos, or what we can do is go in and say, if -1 is a 0, that means that x plus 1 is a factor, and so we can divide f of x by x plus 1 to get some other factors, right? So let's divide f of x by x plus 1, and let's do it synthetically. Okay, so what we're going to do, since we're dividing by x plus 1, we actually use -1 in the box. So it goes back to whatever the 0 on the graph is. That's what actually gets plugged in here. And we're going to hope that we get a remainder of 0 when we do the synthetic process. That'll confirm that -1 really is a 0. Okay, so let's just carefully get all those coefficients in. Let me make sure that was a 10 there. Okay, and make sure we're not having any typos or anything, right? So it's 3x to the 5th minus 4x to the 4th minus 10x cubed plus 10x squared plus 7x minus 6. All right, and let's go through synthetic. So even though there's a lot of numbers, synthetic division is just going to involve adding and multiplying, so it shouldn't be too bad. So we'll bring the 3 down. Okay, 3 times the -1 is -3. Then we get -7. -7 times -1 is 7. -10 plus the 7 is -3. Okay, -3 times the -1 is +3. This is a 10 here, I know that looks sloppy. 10 and 3 is 13. 13 times the -1 is -13. Okay, 7 and the -13 is -6. And then -6 times the -1 is +6. So we do get our remainder of 0. Okay, so that kind of confirms that -1 is one of the zeros. And remember, there's going to be 5 of them here. Okay, so we now know from the division problem, we are going to get a 4th degree term, or expression. So it's 3x to the 4th minus 7x cubed minus 3x squared plus 13x's minus 6. Okay, that's going to be a factor as well. Okay, x plus 1 is one of the factors, and then this big answer we got is another factor. Okay, here's what we can do now. From the graph, it appears that +1 is also a 0. Okay, so let's check it out by doing synthetic substitution. So I'm going to use +1 now and use the new coefficients that we just got and see what we get here. Okay, and let's see if we get a remainder of 0 again, we know that +1 is also a 0. So we'll bring the 3 down, multiply by 1. -7 and 3 is -4. Times 1 is 4. -3 plus the 4 is 1. Did we make a mistake? Brought the 3 down. Let's see, what are we doing? Let's take a look. Brought the 3 down. 3 times 1 is 3. -7 plus 3 is -4. Oh, sorry, that's -4. That's what it is. I knew something was happening here. So that's -7. -7 times 1 is -7. 13 in the -7 is 6. 6 times 1 is 6. Okay, and I knew we were in trouble because we weren't going to get that 0 there unless I caught that mistake. So that's kind of something you guys can do. You know, make sure that you're going to get a 0 remainder. And that confirms that x equals 1 is actually a 0. Okay, because again, just because the graph looks like it was at 1, you either need to go to the table or, you know, look on your calculator and make sure. But this process verifies that actually x equals 1 is a 0. Okay, and then it appears as well, we might have another rational one at +2. Let's check out x equals +2. Is x equals +2 a 0 as well? Let's do synthetic substitution again, right? And let's see what we get. So if we use 2 in the box, and I'm going to use these answers now because this is a factor as well. This is now a 3rd degree. So 3x cubed -4x squared minus 7x plus 6. And let's hope we get a 0 remainder here as well. So bring down the 3. 3 times 2 is 6. -4 plus the 6 is 2. 2 times the 2 is 4. Negative 7 plus 4 is negative 3, and negative 3 times 2 is negative 6. So we do get our 0 remainder here again, which is good. Okay, so that confirms that x equals 2 is a 0. Okay, so we saw the 3 on the graph, the 3 zeros. Negative 1 is one answer, positive 1 is an answer, positive 2 is an answer. Now there's two other ones. Okay, now those appear to be in between. Okay, so what we need to do is we need to use this bottom quotient that we just got right here and find the two zeros from it. Okay, so again, let's kind of recap. We started out originally, the original f of x up here is a 5th degree. Okay, when we did our first synthetic substitution, we got a 4th degree. We did it again. These red numbers here were coefficients on a 3rd degree. So that means now down here we are at a 2nd degree, okay, which is also known as a quadratic. So the 3x squared, taking these coefficients, is just a simple quadratic expression that you can use the quadratic formula on, or you could try to factor it. I'm just going to suggest going right to the quadratic formula. Okay, negative b plus or minus square root of b squared minus 4 times a times c all over 2a. And let's see what the other two zeros end up being. So we're going to get a negative 2 plus or minus. We got the square root of 4 minus 4 times 3 times negative 3 is going to get me negative 36. So we have 4 minus negative 36 all over 6. Okay, 4 minus negative 36, of course, is 40. And let's try and break that down some, see if we can get simplified answers here. The square root of 40. So I know 40, okay, I'll just do this on the side here. Perfect square that goes into it is 4 times 10, right? And that's going to work because 10 doesn't have any other perfect squares that go into it. So the square root of 4 is 2, and the square root of 10 is just the square root of 10. So this is going to be negative 2 plus or minus 2 times the square root of 10 all over 6. Okay, and since each coefficient in the numerator over 6 is reducible, I'm going to go ahead and reduce them. Let's just split it up first. That might help. Okay, I'm going to put each term over 6, and then we can reduce and get final answers of negative 1/3 plus or minus root 10 over 3. Okay, that's one way to write it. If you didn't want to split it up, you could have just left it as negative 1 plus or minus root 10 all over 3 as well. Okay, either way is totally fine. Again, I just knew to do that last step because each of these could be reduced. Each of the coefficients is divisible by 2, and it would actually, it might even be better just to leave it like that as a combined fraction. But once we get into complex numbers later, they do get split up. So either way, but point being, these are your other zeros that the graph shows. Okay, remember there was two other ones that we hadn't used. We look up here. There was one right there and the other one just before the 1 here. These are the exact value of the decimals that these would have given us. Okay, because again, we need to keep these exact. This is considered exact. We didn't round a decimal or anything. It's an exact value. Okay, so that's the process. You really need to go to the graph first, use a rational zero, do your synthetic process. Sometimes you have to do that again and again until you get down to a quadratic. Then that's when you're going to get the quadratic formula out, and you're going to be able to get the exact values for the other ones. Okay. Now some graphs, again, all the zeros might be rational, and you can just get them all right from the graph and not have to worry about quadratic formula. It's just that if you're getting those never-ending decimals when you look at the graph, those are not exact values. That's when you have to go through this entire process. Okay, so those are the real zeros of polynomials.